I'm Julia from Unthinkable, and today I'm really excited to be learning physics with the one and only David Chandler. So thank you very
Actually, it's
much.
not the one and only. There's a bunch of David Chandlers out there, and I keep bumping into them. But go ahead.
Fair enough, fair enough. What I should say is the one and only David Chandler, who you may have seen in my favorite 9/11 film, Explosive Evidence, that was put out by Architects and Engineers for 9/11 Truth. David Chandler is one of the folks who, as I understand it, was instrumental in getting NIST to do a little bit of extra work. Is that right?
Well, yeah, it was a team effort, and a lot of people credit me as though I'm the only one who did it. It was definitely a team effort. But I happened to be in the right place at the right time, and I got a bunch of notoriety piled on me because of it. But it wasn't just me, so I just want to emphasize that.
Well, I think that's cool, giving credit where credit is due. I really appreciate the work you've done and the work of architects and engineers. It's like the first stuff that I started hearing about 9/11 that really deeply made sense to me. That was around a little bit after the time that I had taken college level physics. I don't remember a lot of it, but I'm still really interested, and I'm hoping to learn more about understanding things about the World Trade Center, and hopefully maybe this video will inspire other people to be interested and find out that that's accessible to them too. So thank you for doing this.
So what we had talked about was doing just basically a little intro physics lesson. And this is pretty much, I always have said, all it takes to really understand NIST's fraud, in other words, the fraudulent claims that they made and all that, is high school physics. In fact, it's stuff you'd encounter in the first month of school. So I'm going to basically do a little intro lesson. I get a lot of people that talk about high school physics as though everybody's taken high school physics.
Mm-hmm.
Well, having taught high school physics, I know a small percentage of the student population actually takes it. And of those, a small percentage actually completely internalize it and remember it years later and so forth. So I think this, if worst case scenario, this is a review, but I'm going to lay the foundations for studying motion, and then presumably in a future, maybe we might do 2 or 3 of these, I don't know.
Yeah, that'd be
cool.
cool.
Future one, I might get into, actually doing some of the tracker measurements and so forth, because I can just say right now, I have a kit on my website. My website is 911speakout.org. And if you go on there, and there's, I think, one of the tabs, if you look down at the bottom of it, it'll say physics tutorial or something like that. And if you go in there, you can download a zip file that contains the videos, the calibration data, a tutorial, and links to download Tracker, which is a free download as part of open source physics. And anybody who's interested and has sort of minimal technical skill to be able to manipulate a little graphics program like that, you can duplicate the measurements I did for yourself. If you think that I did something wrong, do it yourself. And if you want to extend what I did to other things, like you were talking about, wanting to know, you saw one of those squibs coming out, you want to know how long it is, well, that's a really easy measurement. And you could also measure how fast it zipped out there. So if you want to know, I did that on an early one, and I got a number like over 100 miles an hour. It was shot out.
Wow.
But the one you had was a nice big long spurt of stuff. The point being, this is not just sort of a passive, a bunch of air pressure relieving through the windows or something like that. So, I mean, there's all kinds of, in fact, the early measurements I did were not acceleration measurements. They were just measuring everything. Here I have a tool, and when you have a hammer, everything looks like a nail. Right? So I basically went around measuring everything that was measurable just to see what's interesting. And I happened across some things that were pretty darn interesting. And it
Tracker
blew me
is fun.
away when I heard rumors that the Building 7 came down at free fall, but I never saw a convincing measurement of it. And I just said, well, people are, it's a seat of the pants estimate.
Mm-hmm.
And when people say how many seconds it takes to come down, you can't even see when the thing hits bottom.
Right.
And that's not a significant number anyway. So yeah, it's just, it's very fast, like they say 7 seconds or whatever. I've never measured that, but that's not what's really critical. What's critical, if you want to say how fast does it come down compared to the acceleration of gravity, you need to measure the acceleration of the building to compare it to the acceleration of gravity, which is something NIST didn't do, at least early on, until we sort of put them in the corner.
Yes, that is literally how I think of it. They put NIST in the corner.
But they are continuing to lie, and I want to bring that out in the end. They basically acknowledged what they had to, and then they continue to lie about it. So they're lying about the significance, et cetera. So anyway, there's a lot to be said there. And
Yes.
by the way, I had made these measurements early on with a very crude tool that I just happened to have available. It used to be called World of Physics, and it was basically for doing measurements on amusement park rides and stuff like that for a physics class. And I was able to, I communicated with the author and figured out how to import other videos into it, but it was very limited in what I could do with that. But that was good enough to get the job done at that time. Since then, I found this really good tool called Tracker, and it's part of the, if you want to look it up, Tracker won't find it for you. You have to say Tracker and put in also open source physics.
Yes.
That will get you this tool. And
I recommend it. I've got it. I've been playing with it.
Yeah, I've been encouraging you to actually play with stuff like that. So, okay. So if I'm going to go ahead and go to doing my little intro song and dance about measuring motion, as I would in an introductory physics class in the first couple weeks of class. All right.
All right. I'm going to take a few notes.
All right. And share my screen here.
I see your screen.
Okay, good. All right, so I don't know if you can see that, but there we go. All right, so if you're going to measure position, we start with a variable for measuring position. So let's just say X. Normally use X when you're measuring horizontally, Y if you're measuring vertically. They use the letter S referring to space if you're using it in general, so it could refer to either horizontal or vertical or whatever. So there's various symbols you could use for all that. Then when you're measuring the rate of motion, that's speed or velocity, and there's a difference, but they're very close to each other. And since speed and velocity are so close, we just use the letter V. At least in physics, we just use a V. And the difference is that speed is what they call a scalar. That's something that's just like represented by a number. So how fast, right? And if you use velocity, you put a little arrow on top of it like that. That indicates that it's a certain speed in a certain direction. So in other words, this velocity and this velocity, they're different velocities. Even if the arrows are the same length, they're in different directions. And if I want to say what's the change in velocity, I would look at, here's V2 and here's V1, and there's the change. You could say delta V. That's the delta is the Greek letter, that little triangle.
Change.
That's for a difference. It's D for difference, but it's a Greek letter D. So it's the change in some quantity. And so we'll use deltas quite a bit. All right. And in fact, the definition of velocity, so these, by the way, they could also be given with vectors, but we're not going to mess around. I'm not going to be too formal on that. So I'll just use that. So the velocity or speed, either one, is going to be the change in position over the change in time. All right. So that's your definition of velocity. If you use the vector versions of these, that's velocity. If you think of it like miles per hour. When you say per, it's for each, and it's like a division, right? So say you go 60 miles and it takes you 3 hours. Well, 60 divided by 3 is 20 miles an hour, right?
Yep.
So the delta x over delta t, that's how you come up with your velocity. And the units follow the same pattern. So this would be meters per second, miles per hour, kilometers per second or minute or hour or whatever you want.
Yep.
Something per year, whatever. So a distance unit divided by a time unit would give you a speed or velocity unit. Okay?
Okay.
Now, there's another quantity called acceleration, which is defined in a very parallel sort of way. And acceleration is basically talking about how quickly your velocity changes. So that's going to be delta V over delta T, all right? So if you start off going at 20 miles an hour and you decide to pick up some speed and you build up over 3 seconds, you build up another, I don't know, 15 miles an hour, all right? So you're basically picking up 5 miles per hour each second. So this would be, so delta V would be 5 miles. Well, actually it would be, let's just do it out. So it'd be 15 miles per hour over 3 seconds, okay? So that's your delta V over delta T. Your acceleration going down the freeway, picking up 15 miles an hour in 3 seconds, that would reduce to 5 miles per hour per second. So it has more complicated units because it's not a distance per unit time, it's a speed per unit time. So it's a speed unit per unit time. And so this is sort of a mixed time unit, hours and seconds and all that. But you could do the conversions and convert all the distances to a uniform thing. In lab measurements and stuff, we talk about meters for distance, and all the times we convert into seconds. And so since that's meters per second, we abbreviate it. This is an abbreviation, meters per second squared. But this would be an acceleration kind of a unit because it's a distance unit over a time unit. In other words, a distance over time would give you your velocity, and the divided by time gives you your denominator here. So
yes. So
just keep in mind, this is meters per second of increase or decrease or whatever per second. So, all right. So you can't ever talk about the acceleration of gravity is meters per second or feet per second.
Meters per second squared.
Unit. So it's how many meters per second increase each second would give you your acceleration. Okay. So far, so good?
Yeah.
So now I'm gonna just go to a clean sheet here. If you graph position versus time, all right? Let's just say we're increasing. So here we started at a certain place. In other words, here's 0. So say we started, so here, picture, here's where we're measuring from. Say that our little cart or whatever it is we have here is starting at a certain place, call it X naught. By the way, NAUGHT, naught, is that little subscript 0 somehow or other. In physics and engineering, a lot of sciences, they talk about that as something naught.
I learned that in a Star Trek episode once.
Saying 0.
I learned that in a Star Trek episode once.
Okay, well, X naught, V naught,
yes.
That just means your initial velocity, but the naught comes from sort of the fact that there used to be this British Empire that we were all part of, you know? So,
I've heard of it.
So anyway, this distance here would be your X naught, right? That's your starting point. And then notice that as time goes on, the position keeps increasing. So here you're at that position, and here you're at that position, and so forth. And so if I talk about if I go back and remember that velocity is delta x over delta t, well, this is, if that's a straight line, in other words, it's a uniform velocity, which is not to be assumed, but assuming just for simplicity, that's a uniform velocity. And here's your delta x, and here's your delta t, right?
Yes.
And if you take the rise over the run, you learned in Algebra 1 that that's called the slope. Okay, so the slope of this line has physical significance. That's interpreted here as your speed or your velocity, all right?
Yeah.
So finding the slope of a straight line graph frequently has some sort of physical interpretation. In this case, the slope of a position versus time graph gives you your velocity. And since it's a straight line, it means it's a constant velocity. So if you took any 2 points on the line and you take your delta x over your delta t, you should get the same ratio. You might have a different amount of delta t and a different amount of delta x, but when you take the ratio, one over the other, that ought to come out the same ratio as this because your slope the same, and constant slope is what makes the line straight, right?
That makes sense.
So far, so good?
Yeah, I get you.
Now, what about acceleration? Well, on this kind of a graph, if you're accelerating, well, look what you have. You have on this a straight line for, and that means your velocity is constant.
Right, so
So if
you're
your
not
velocity
accelerating.
is constant, you're not accelerating. So acceleration is 0, right?
Yeah.
Now, let's do a different graph. So what if my graph looked like that? All right. So here I'm starting out. If I say that's level and it goes up like this, all right. Well, here I'm starting off. If I do a tangent line to this curve, here's going to be v equals 0. And then maybe here I have a larger v. And up here I have a larger v. You can see how the slope's increasing?
Yes. And
so acceleration on this kind of a graph would be indicated by the curvature of the graph. And so it's the faster this thing picks up speed, the more the slope increases, and therefore you get curvature. And if it's an upward curvature like this, that's a positive acceleration. So this might be a car pulling away from a stop sign, and you're picking up speed as you go down the road, right? Okay, so far so good?
Yes, I get it, makes sense.
If you have a more general kind of a graph where, like say, position versus time, it could look like this, for instance, right? So here you have starting off at rest, here it's picking up speed, now here it's losing speed, here it's at rest again because there's no slope, and remember the slope indicates your velocity.
Yes.
Here's how far you've gotten. That height represents how far you are. But now you're going very steeply negative, and you sort of level out again, and then you're going negative again. So in other words, you can track along, and the height of the graph, the position on this graph indicates where you are. The slope of the graph at a particular point indicates how fast you're going. And then if you talk about the rate of change of slope, so here notice that the slope is going from positive to 0 to negative.
Yes.
So in this kind of a region, A is less than 0. So if you're slowing down, or at least you're accelerating in the negative direction. All right. In fact, you're slowing down as you go forward, but you're actually picking up speed as you go backward. So all of that's like negative acceleration. And here it's like positive acceleration again. Here it's positive, and so forth, right? So acceleration would be the changes in the slope, and each one would be a rate. So you say, what's the speed here? What's the speed there? How much time in between? And how much did the speed change per unit time? And so forth, all right?
Yeah.
However, when you're talking about acceleration, it's actually easier to change your graph. So for instance, what if instead of plotting x versus t, I plot v versus t? All right.
Okay.
So what would a constant speed motion look like on this graph? Well, if it's constant speed, pick out what the constant speed is going to be. Call that v naught, which is going to be your constant speed. There you go.
Yeah.
It's the same speed everywhere. And so it's just a level graph, right? Now, remember a minute ago, we talked about an x versus t graph. A constant speed looked like that. So it's a straight line, and whatever the slope was told you what the speed was. But on this kind of a graph,
I think I know where you're going.
by the actual value of the function. It's the actual height of the graph. So this is your speed, and over here, that slope is your speed. You see?
Yes. Is on this graph the slope going to be the acceleration?
Well, let's figure it out.
Okay.
So right now, that's constant speed, so there's zero acceleration. So these could be two graphs here illustrating exactly the same motion, for instance, right?
Yes.
And as we said a minute ago, if it's a straight line on x versus t, it means there's no change in the velocity as you go along, and therefore it's constant, it's zero acceleration, it's constant speed. Here, constant speed is indicated by a constant height on the graph. And so again, there's no acceleration. Okay, so what if I make a little change? What if I do velocity versus time? And this time, let's say we have a slope on the velocity graph. Okay, what's happening here? Well, on a position versus time graph, we would say we have this speed, which is this slope initially, and now we have a bigger speed, and so it's a steeper slope. And here we have a bigger speed, so it's a steeper slope. And so it looks like we have a graph that's curving upward like that somehow, right?
Yes.
But on a velocity time graph, could still be a straight line graph. And notice what this is. This right here is delta V. Somehow my graphics tools adds those little extra gotchas for no good reason. I think it's the, all right, so this is delta V because that axis is V. Here's your delta T, right?
Yes.
All right, and we said that acceleration is delta V over delta T. Well, what do you know? That's the definition of slope when you come to this kind of a graph, isn't it?
Yeah. Yep.
So, so now we have, we've gone through two kinds of graphs. We could actually do three. So we could have an X versus T. We could have V versus T, and why not go ahead and throw it in? We could have an A versus T. And so here, if I have a straight line here, that indicates a constant velocity. And so there's your constant velocity, and that would be a zero acceleration, wouldn't it?
Yes.
So that's the same exact motion described on these three different graphs. Your acceleration is zero and stays zero the whole time. Your velocity is a constant and stays constant the whole time. And here, the position is increasing, but it's increasing at a constant rate, so you have a nice straight line graph, all right?
Got it.
So there's an interesting relationship here, is that if I go from a position graph to a velocity graph, the slope here gives you the value of the graph there, right?
Yeah.
So you can make a transition from here to here by figuring out the slope everywhere. And here, the slope everywhere is the same slope, so it's a constant, right? And it's the same relationship here. Because the slope is zero, slope is still zero, slope is still zero. So if I take the slope of this graph, I get zeros everywhere up here, don't I?
Yeah.
So the relationship among these three variables, x, v, and t, there's a term in calculus for this relationship. So v is considered to be the derivative of x, and a is the derivative of v, all with respect to t. So we're saying something versus t, so time on the horizontal axis. So the derivative of this function gives you that one, the derivative of this function gives you that one. So those of you who have a little calculus, this is what the terms are. If you haven't had calculus, this is actually what I consider one of the best introductions into what calculus is about. There's a lot of people who take calculus who never had physics. And I wonder what's, they must just be floundering around. What's all this stuff about derivatives and stuff? When would you ever use this? Well, we're starting by using it. And by the way, here's what you call it, all right? So, but right now, so if in a high school course, we would actually be doing the same thing, but we're not doing in perfect generality. Here is a very simple motion where that's a straight line graph, all right? We can go up one notch and still keep it within the realm of high school math, all right? So let's go one notch higher in complexity.
Okay.
Which is this, A versus T, V versus T, and X versus T. And again, X could be X or Y or S or whatever, depending on horizontal, vertical, or do you care, okay? So rather than keep a zero acceleration, see, this is what you get in Algebra 1. You have a constant rate. Remember that equation, D equals RT? Remember from Algebra 1, distance equals rate times time?
Oh, sure. Yeah.
If you can remember back that far, all of these word problems you get in Algebra 1, this is one of the equations they have you using, right? And that rate is the same thing as our velocity. And there's your distance and there's your time. Well, all of this is assuming constant velocity. So this is the situation that you had in Algebra 1. But if we're going to do this in a physics course, we like to bump it up one notch at least, so that you can get a little bit more power to what we're doing. So here, let's not have a zero acceleration. Let's have a constant acceleration, okay?
Okay.
And so there's my A naught, or I'll just make that the constant acceleration, right?
Okay.
So what do these graphs look like if the acceleration is a constant? Well, what's the relationship between A and V? Well, A is the slope of this graph. And so here, if we have a constant acceleration, what does that tell you about the slope of the graph here?
It's going to be like a positive.
It's going to be sloped,
yeah,
but it's going to have a constant slope.
Yes.
Which is saying it's going to be a straight line.
Straight line, right? Yes.
Okay, so this kind of a acceleration versus time graph corresponds to this kind of a velocity versus time graph. So here the velocity is not constant, and you couldn't do it in your Algebra 1, but you could do it, actually you can do it later in Algebra 1, but they just don't run you through it as enough. But then look what's happening between velocity and position. Here we have a certain velocity. Here we have a larger velocity. Here's still larger, still larger, still larger. And those velocities are interpreted as slopes down here, aren't they?
Yes.
So if here I have some velocity, and then I have greater velocity, and then greater velocity, and greater velocity, you can actually work out what just happened on your end. I don't know.
Oh, I'm showing you that I'm getting it.
Oh, okay. You can actually prove that this is going to be a parabola. Okay. Now, so we just sort of went down the scale from acceleration to velocity to position. But if you did this, if you start with a parabolic graph, and if you look at how the slope changes, you'll find out that the slope changes the same amount in every increment of time. And so it'll be a nice constant slope for your velocity. And since that's a constant slope, that's a constant acceleration there. Okay, anyway, just realize these are three distinct concepts. They have their own units, meters, meters per second squared. Okay, they're referring to different things about the motion, right?
Yeah.
And there's a mathematical relationship. Somehow the relationship is tied in with these slopes, right? Okay, now let's figure out how to actually do this translation. So what if we started with A and I want to find V?
Okay.
All right. So let's see. If I say A is delta V over delta T, all right, that's our definition of acceleration, right? Then that means that delta V, just doing some algebra, is equal to A times delta T, right? Just multiply both sides by the denominator.
Yes.
So far, so good?
Very good, yes.
Well, let's see what that looks like geometrically up here. Here's your A, it's the height of the graph, which is a nice constant, isn't that handy? All right. And then delta T is like this, right?
Yeah.
Geometrically speaking, what are we doing when we take A times delta T?
You're calculating the velocity change.
Well, yeah, that's what we're trying to do. But geometrically, what does it look like up here?
A rectangle. I mean, it reminds me of when we learned about integrals.
Yeah, in fact, that's a word we'll introduce at some point. But just to put it in simple terms, isn't that what you do to find the area of a rectangle?
Yeah.
Length times width, right? Height times length, or whatever you want to do. So if A is your constant height of this rectangle and delta T is your length of this rectangle, A times delta T is given by the area of this rectangle. Now, in calculus, you call this the integral. Mixing upper and lower case there. Anyway, that's your integral. And it makes sense to give it a different name because, you know, if this were really an area, you'd expect it to have units like square meters or something like that. But here are the units of this region for this. When we do the area type calculation on this region, you're taking acceleration units times time units. So the units of this quantity that we just calculated is actually velocity. And so you don't usually think of an area equaling a velocity, but the area is representing a velocity. And so the more general term that they use in calculus for this process, they don't literally say it's finding an area, although you get into saying that all the time. But I mean, actually what you're doing is you're calculating an integral, but that integral is found by, just think of it as equivalent to, it's a generalization of the idea of an area calculation, okay?
Got it.
Good enough?
Yeah.
All right, so basically, I'll just use the term area here because it's simpler. So by finding the area under this graph, it gives you the speed. So that gives you the value, the height of these points on this graph. All right, so in other words, if I take at this time, the area is this amount, and I would plot that area as a point on this graph. Then if I go to this time, I would say at this time, here's my area, and that's a larger area, so I'm at higher on this graph, you see?
Okay.
And then at this time here, I take this amount of total area, and that gives you the height of this one, and so forth. And so if I have a constant acceleration going equal increments of time, you're adding equal chunks of area, aren't you?
Yeah.
And so by taking the area under the acceleration graph, you're getting the velocity. Now, what about how do you get down from velocity to position? Well, if we're going to use the same concept, maybe finding the area under this graph would be relevant, right?
Yes.
And in fact, let's see that it is relevant, because if I took let's just take a very thin slice of this, extremely thin. In calculus, you say that's differentially thick slice, just a very, and the limit is it's almost zero width to it. Not zero, but just very tiny, right?
Just approaching.
It sort of looks almost like a rectangle, doesn't it?
Yeah.
Because this height's almost constant over a very short time interval there. And we just saw that finding the area under this graph, I mean, since these are all in the same relationship, in other words, slope, looks like it ought to be area, right? Well, if I take the area under this little thin slice, that ought to have, let's see what the units of this are. The height of this rectangle is in meters per second.
Yes.
The width of the rectangle is in seconds. And if I take meters per second times seconds, I get meters.
Meters, yeah.
So the thickness, so the area of this little slice looks like it's actually a distance, which I'll have to plot directly on this graph down here. You see?
Yeah.
And if I say, well, let's take the next little slice. Okay. So I have to adjust my height a little bit, but if I keep up adding up the slices, overall, that's like finding the area under this kind of a region. And the area under this region can be, on one hand, can be thought of as the summation of all of these tiny infinitesimally thin slices, right? You don't want to add up an infinite number of infinitesimal slices, but if we can come up with the same area some other way, we're good to go, right?
Yeah.
And since we're limiting ourselves to horizontal lines and straight lines and stuff, ordinary geometry ought to give you a clue on how to find this area. What is this shape called? I'm testing your geometry memory now.
That thing?
Yeah.
What am I going to call that?
Well, the conventional.
It's a polygon.
It is a polygon. It's a four-sided polygon. Two sides are parallel. Two sides are not parallel. And that's called a trapezoid, all right?
Oh, sure. My 4-year-old son would have probably gotten that right.
All right, so that's a little geometry review. However, you could also think of it as a rectangle plus a triangle, if you sliced it like that.
Okay.
So one way of finding the area is to divide it up and find the area of the rectangle and then add the area of the triangle and you got it. But there's a direct way to find the area of a trapezoid. And it's actually, you know, they probably don't teach it to you this way. They give you a messy looking formula in most math classes I've seen, but it boils down to a very simple formula, which is the two parallel sides are called bases, because usually they portray a trapezoid this way. So you have the two parallel sides on the top and bottom. Here it's on the sides, right? So these are called the bases, and this distance in between is called the height, because you see that would be your height. Okay, so here's your B1 and here's your B2 and there's your height. They give you a formula involving B1 and B2 and the height, but there's a simple way to see it. Simply, here it comes, average the bases times the height. So if you have a trapezoid, take the average of the bases times the height. So for instance, if here is one base, here's the other base, you could think of it as, so this is the average of the two bases is this.
Uh-huh. I see that.
And here's your height, right? So just put this triangle over here. So to find the area of a trapezoid, just average the bases times the height. In any case, one way or another, or you could split it into a triangle plus a rectangle or whatever. You could use one of the formulas that you get out of it. There's several different approaches to this. Okay?
Gotcha.
And I'm just talking about the specifics of this particular shape. In general, you'd have to find these areas by various means, including calculus, if it's not a regular thing, all right?
Mm-hmm.
So right now, we're just keeping the problem simple enough that you don't need to go that far. And so there you go. So we know how to find the area at least. And the point is, if I go at this time, we find this area. And the value of that area or integral gives you the height at that time. And at this time, you would find this area, and that's the value. The value of the area gives you the value of the height position at that time, you see? So there you go. We have a pair of operations that allows us to move from position to velocity to acceleration graphs, and from acceleration to velocity to position graphs. You go slopes going this direction, you do areas going this direction. So what is calculus about? Calculus has two fundamental problems. One is finding slopes of curves, and one is finding areas under curves. And why those two functions? Well, it looks like they are inverse operations of each other.
They are.
You can use one set of these to go one way and the other to go the other way. And so this is a capsule summary of what calculus was all about. So if you took a calculus class and never figured out why you're doing all of that, you're basically learning how to do these kinds of problems in general. So for instance, in general, you might have an acceleration versus time that looks like that. And you want to find, where are you? So for instance, if you're taking inertial navigation, like for instance, in the flight data recorder, what it records is the it has an accelerometer in there, and it's talking about the acceleration as a function of time. And it's going to vary all over the place. You're going to pick up speed and lose speed, and it's going to be different in each of three axes and so forth. But you want to get from acceleration to know how fast you're going at any moment. So what do? You're going down the slope here, you integrate. So this is integration, or finding the area. So by finding the area under this, by various numerical techniques that you can do without even knowing calculus, you just take little tiny thin slices and add them all up, you're finding the area. And you can come up with a velocity graph that corresponds to that. Then you do it again, you integrate it again, and you can get where you are. Okay, so you can keep track of your position, and all they really measured was your acceleration. All right, so that's another example of doing this kind of thing on a computer, where the technique for doing these operations is by taking little tiny thin slices with a few little tricky refinements to keep it more accurate, basically. And then there you go. All right. So let's come back. And so the problem at hand is we want to deal with the simple motion, like say a dropping ball. So you drop a pebble into a well, or you throw a ball upward and you want to track its motion, right? So you can measure, think of a rock. You throw a rock straight up, all right?
Yep.
And you want to measure the height as a function of time, and then you want to figure out the speed as a function of time. And in the case of throwing a rock up and down, the only force acting, assuming air resistance is negligible, the only force acting would be gravity, which is a constant. So that's a good example of this kind of a problem right here. We have a constant acceleration, velocity that varies linearly, and position that becomes a quadratic equation, which is why that plots out to be a parabola. All right, now here goes. I'm going to derive the equation that NIST puts in their Building 7 report that is badly abused. I mean, they know better. It's not that they should know better, it's they do know better, but they used it anyway, which is why I call it fraudulent. It's not incompetence. You can't use incompetence theories dealing with NIST, because they're not incompetent. So if they did something, they did it intentionally, knowing what they're doing. And anybody who touched that part of the report knew that they're participating in a cover-up. That's what I'm going to get at. So let's start with an acceleration versus time graph, and let's limit ourselves to a constant acceleration.
Okay.
So this is like for throwing a rock into the air. Okay.
I have a question about the throwing the rock in the air.
Yeah.
It makes, like, I get it if you're saying like dropping the rock.
Yeah.
But throwing it up, like the other forces like you throwing it up, and then are you talking about just from, tell me, am I missing this?
Yes, you're missing this.
Okay.
So what's going to go on is if you throw a rock straight up, the rock is in free fall immediately when you let go of it. All the way up, over the top, and back down the other side. And we'll see that when we get to using tracker, okay? But just to show you here, here, let's put that off. Put that one on hold,
okay,
and we can come back to that. But so that's my point is your downward, in fact, if you do a velocity versus time graph when you throw a rock straight up, you can't even tell when it gets to the top of the, it doesn't look like, it doesn't change in any way. It's a straight line graph throughout. And there's an interesting reason for that. But that's getting a little bit, that's getting into some of the interesting stuff that unless you've gone over it a few times, it seems counterintuitive at first, right?
Okay.
There's a lot of stuff in physics that's counterintuitive because you're starting out with a man on the street intuition of physics. I mean, you know, everybody who comes into physics has a complete worked out kind of physics in their head because, hey, they crossed the street without getting killed. They got their fork from their plate to their mouth without stabbing themselves in the face. You know, they had some idea of how the world works.
Yeah.
But their intuitive idea is built on concepts that are not perfectly general and don't really work in the long run. So it's good enough to get them through life, through the day, and assuming that they're just going to be doing menial things versus creative things with the physical universe, like being an engineer or something, then it's good enough for some purposes. But the purpose of doing Newtonian physics in a classroom is you're going to come down to principles that will apply across the boards. All right.
Okay.
So that's our goal here. All right. Anyway, I'm going to start with this, and I want to do this algebraically. So given your acceleration, so acceleration is a constant, right?
Yeah.
Once I know that the acceleration is a constant, velocity is a function of time. We know it's going to look like that because we've been over this ground before. This is V naught. And this is, we decided was A times delta T. That was the area up here, right?
Yes.
A delta T. This gives us how far we have, how much velocity we have gained or lost. This is how much velocity we've changed.
Mm-hmm.
Well, here's our starting velocity, and then here's our change in velocity. Our overall velocity here is V naught, that's our starting velocity, plus A delta T. Does that make sense?
It does, but I'm thinking about it.
Okay.
I have to like let this.
Okay. Well, people can pause the video and think about it, right?
Yes.
But
We
so
can
in
keep
other
going.
words, all right. So basically, you starting off with some velocity, and so that's like this baseline of this figure here. And then you've increased your velocity because you're accelerating.
Okay.
And so, in fact, find the slope of this. If I find the slope of this line, then the difference here is A delta T, and the difference here is delta T.
Okay, yeah.
And A delta T divided by delta T, rise over the run.
Uh-huh.
Delta T's cancel, leaving you A.
Yes.
slope is
I
A.
got it.
Okay?
Yes, 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 yes.
So this gives us an equation that I'm going to write down. So delta V is equal to, or just say your new V is going to be your starting V plus A delta T. All right.
Okay.
That's basically what I have right here. So far, so good.
Good, yeah.
Let's go to the next step. Where are you as a function of time? Well, we have to find the area under this graph, don't we? So first of all, we might be at some starting position. So here's X naught. And then we know that's going to look sort of like a parabola of some sort, but let's just draw it in roughly like that. And then we can say at this time, what's the area here? Well, how do I find, so that's going to give us this basically. X naught is our starting point. This doesn't know anything about our starting point. So the amount of position that we have changed from our starting point is what's given by this area. All right.
Yes.
So this is giving us our change in position. So here's our starting position, and then we want to add this to it. Okay. So if I want to find the area here, we know we average the bases times the height because that's a trapezoid, right?
Yeah.
Or I take the rectangle plus the triangle if you prefer. You want to take rectangle plus triangle? Is that a little more comfortable?
We can do that, yeah.
Okay, so what's the area of the rectangle? Well, that's V naught times delta T, right? So I'll just say delta X would be V naught delta T. This is our delta X here, right?
Yes.
That's V naught times delta T. That's the rectangle. And then the area of the triangle is 1/2 base times height, isn't it? 1/2 delta T, which is the base length here, times the height, which is A times delta T, right?
Yes.
One half A delta T squared. So this could be X minus X naught equals V naught delta T plus 1/2 A delta T squared. Okay. Now, if I add X naught to both sides, okay.
Okay.
So I have two equations I've come up with. I'm just going to write them down here. We have V equals V naught plus A times delta T. We derive that equation. And then we have X is equal to X naught plus V naught T plus 1/2 A delta T squared, V naught delta T. All right. So let's go back. Here's the one. Position as a function of time. There it is. There we are. V equals V naught plus A delta T. That was simply by going from the area graph to the velocity graph, right?
Yeah.
And then going from the velocity to the position graph, we come up with this equation. And there we have it. Assumption. Assumptions. What was assumed in order to come up with these equations? There are some people, many people, even people who should know better, who just take these two equations and just plug stuff into it, right? But there's assumptions built into how we derive these. So if we go back and look at this, here's our assumption right here.
Constant acceleration.
Yes.
I see it. I get it. I see it.
So starting from the assumption of constant acceleration, we're able to come up with this equation for velocity at any time and this equation for position at any time. Now, let's go to dropping a rock down a well. So here's your well. Okay. And so here's my rock, and I let go and I time. So we have a delta t for how long it takes to hit the bottom. You listen for the rock to hit the bottom, and you want to figure out how deep is the well, right?
Yeah.
So our position as a function of time, what was our initial position? Well, how about 0?
Yeah.
And so we can say that's 0. What's our initial velocity?
0.
What's the acceleration? How about the acceleration of gravity?
9.8 meters per second
Times delta
squared.
t squared, right? So we get x equals 1/2 g. Now, by the way, they frequently leave off the delta on t, and I justify it like this. If you're basically looking at a clock, you want to say how much time has elapsed. You look at the final time minus the initial time, and that's your delta t, right? You're doing a lot of these situations, what you do is use a stopwatch. So I frequently just say, we're just going to use stopwatch time, or use hit starting. So you're automatically starting at 0. So if I take final minus initial, the initial is 0. You can just leave off that little delta. The t is the delta t, all right?
Got it.
That's sort of a shortcut. So it's frequently written that x is 1/2 gt squared, all right? Now, let's pull a NIST. NIST started with this. Let's take this equation and solve it for t.
Okay.
So let's multiply both sides by 2 and divide both sides by g and take the square root. Except I think what NIST used was like maybe h here or something, the height. Look it up in the NIST Building 7 report. This is the time that they call free fall time. What in the world is free fall time? Well, the time this is giving you is the time for hitting the bottom of the well. If you started at the top of the well with x equals 0, with 0 net velocity to start with, and you have a constant acceleration, and you started the clock like stopwatch time. So you started the clock at the instant that you let go of the rock. So this equation assumes you are dropping a rock, you start the clock, t starts at 0 immediately when you let go, and from there all the way down, it's moving with a constant acceleration. What's wrong with that? Well, if you look at the graph, here's the building 7, for instance, going along essentially at 0, or holding its position, and it does this and eventually wanders off, all right? So they're taking a starting point and an ending point like they're starting and stopping a stopwatch. So they took their starting point back here, and their ending point is about here. So what they're doing is they're taking that slope as characterizing the motion. They're taking 2 points and only 2 points. In their calculation, there is no information about anything else in the motion except when it started and when they stopped their clock. Do you see anything wrong with this?
Well, yes.
What was the assumption that they're ignoring?
That
they're ignoring constant acceleration.
Constant, yeah.
Well, acceleration is constant maybe during this part.
Right, and during that
tell from
little
the
part
graph,
there.
the slope keeps this change. Here it's almost zero slope. It is zero slope actually at first. And then here it becomes a constant slope for this little section, because it is free fall actually for this little section. But they're just taking this artificially early start time and this ending time, and that's when they started their stopwatch, and here's when they ended it. And that's their 40% slower than free fall that they came out with.
Wow. Wow.
That is a wow. And the other thing is, what do you mean free fall time? You can't characterize free fall by a time. What characterizes free fall? How about acceleration?
Okay, so I just have a question about the equation there in the box where it says t equals the square root of 2h over g.
Yeah.
Where does h come from compared to what we were working with?
Okay, we had x over here. We did it using x. I had just made the comment that NIST, in their version of this, they plugged in h. That's the same thing as the x over here, all right?
Got it.
So I just changed symbols to make it conform to what's in the NIST report, all right? But it's talking about a distance, a height of the drop of the building, how far the building dropped. All right?
Got it.
So whatever. So it's just another, I just sort of threw that around a little bit loosely here. Okay, so the point I was making is that free fall time doesn't say anything. There is no such thing. This is not a thing. Free fall acceleration is acceleration at this particular acceleration right here, acceleration of gravity. But they didn't measure the acceleration, because if they had, they would have had to graph all this out and then find the, let's just do this, find the slope everywhere along here. And they would have found, whoa, the slope is basically zero here and negative slope here and so forth. And so they would have actually had to plot velocity versus time like I did. And in fact, when they did their final report in November 2008, they actually did that. That was that little funky graph they did that had 3 parts to it. And it was linear here, and it was like curving here, and did something like that up there. And this one they actually acknowledged was at free fall. They even had a little box down here on that graph. I'm just referring to a graph. On that graph, they have 32 point whatever. You know, the acceleration of gravity is 9.8 meters per second squared. But in English units or in conventional units, it's 32 point something feet per second squared. And that's the number they have. But they actually identified the slope here as equal g. So they literally are acknowledging that it fell with the acceleration of gravity, except they had this little transition time. But what is that transition time? It's phony. It's talking about a bunch of time that it wasn't even falling. They had artificially pushed this time back. Now, I have done more sophisticated measurements of this more recently using my better tools. What I have found is what actually happened, if you zoom way in and look at it sort of under a microscope, so to speak, what happened in this time is the center of the building, which is where they're tracking it. They're tracking a point near the midline of the roof, all right? I was using the corner. The corner just goes through a sharp turn, boom, and then boom. But for their midline position, what actually happened is there was a small collapse, and this thing dropped about 1 meter and held. And so it basically, so this part here, there was a point where it dropped 1 meter and held fast. And then that point, if here's your building. So here's their point, here was my point initially. And I also track this point just for comparison. This one gets lost in the smoke very quickly. This one's clear, and that's why I use this point. This is building 7, by the way.
Yeah.
If you recognize it.
I knew it right away.
This point drops about 1 meter and holds tight. This point doesn't drop, nor does this. And then all 3 of these points let go and transition to absolute free fall at the exact same moment within about 1/10 of a second or couple.
Whoa.
All right. So this is a building which is 100 meters side to side. So it would cover a football field overlapping into the end zone. In fact, the width of the building is within 1 foot or 2 of the width of a football field. So just imagine a building with a cross section of a football field. And somehow the opposite ends of that building somehow can coordinate to where they let go and drop within a couple of tenths of a second.
Sounds highly unlikely.
Does not sound like it's a natural progression from, from fire. It sounds like somebody pushed a button. All
I
right?
agree. Yeah.
So this is the basis for, this is a good Solomon. By the way, this analysis, if you go to the recent quote unquote requests for correction that AE and some of the family members and some engineers and all that they put in, I redid my measurements in that. I worked with Ted Walter and AE on this, and there's a whole section in the middle where I did my revised. If you want to look at the best measurements I've done on this subject, it's all right there. And I track all 3 of these points and show what's really going on with a fine scale. All right. So this is above and beyond what I did back in 2008. Anyway, there is your little intro to the physics of 9/11, enough to recognize that what NIST did was so transparently, blatantly fraudulent. And what they're saying now is, well, okay, it was in free fall, but that doesn't matter. It's still consistent with our analysis.
That doesn't make sense though, because...
And Shyam Sundar explained why it doesn't make sense, because he actually, and when he did his, if you listen to the initial time when I got my question asked in front of him, he babbles around for a while and then he settles down and he said, basically it can't be free fall, because free fall is when there's no support under the structure. And there was support.
Right.
And there were many connections that had to be broken, and they didn't all happen at once. So he's basically reasoning that for a natural collapse, it's unreasonable to say it came at free fall. Well, but then you look at the evidence, it did go at free fall. What does that tell you? It's not a natural collapse.
Right.
But he doesn't go there because they're not going to go there.
No, they're not. And I know that they ignored or denied the last request for correction.
Yeah. So, I mean, well, did you expect any different? I know,
No.
but I mean, it's the thing is though, yeah, we're getting everything documented up to the hilt. So anybody at any time from now till the next couple generations, they can look at these documents and they can see that we had them nailed and they are lying through their teeth, all right?
Yeah.
And so that's, for me, hey, I'm not looking at all of this in terms of strategy. For me personally, I'm doing this because I'm trying to uncover truth and I'm trying to speak truth to power. Now, what they do with it, that's their business. But it's unfortunate for this country that they seem to be able to get away with it because just by raw exercise of power, they lie and they have PhDs and NIST has a good reputation and all that. And so people who can't think for themselves will say, oh, they must be right. You're just a high school teacher. Yeah. I know this stuff.
Yeah.
Okay. Anyway, there you go.
Thank you so much for doing this. It makes a lot of sense, and I should have taken high school physics maybe, because it would have made a lot more sense.
Yeah. Well, if you take high school physics, basically, calculus makes more sense too, because here's the problems that calculus was invented to solve. And these are the kinds of problems that calculus was invented to solve. And so it puts it in its context, so it doesn't just seem like an off-the-wall thing.
I took calculus before I took physics in my first year of college, and it was hard but fun. And now that you've explained it this way, honestly, you're right. It does make a lot more sense. So, yeah. All right. Okay. Thank you. Well, this was fun.
I've enjoyed it, and I can come back and show you.
Do it again.
Yeah, I'd like at some point to demonstrate using Tracker, because I put it up there on my website. On my website, 911speakout.org, there's a menu bar across the top, and one of the tabs there is called References. If you hover on References, down at the bottom it says Physics Lab. And in there you can download the zip files that include Building 7. I can't remember, I think I have some other things in there as well. I think if I recall, I put in there some actual known demolitions as well.
Yes, you did.
I also did I do that?
Yeah, you have 2 in here.
So I haven't looked at that for a while, but anyway, so I have some known demolitions, and I have Building 7. I don't remember if I did Building 1, North Tower. Do I have that?
We have North Tower.
Okay. So you can measurements
7.
on all of these things. And I put in the information you need, like the spacing between the windows, so that you can actually calibrate your measurements and so forth. So
it's fun, and it's not as hard as it looks once you start playing around with it. I was struggling with it because I picked videos that were, difficult because of how precise you need to be. But I'm looking forward to continuing to play around with it.
Through it. And it's, I use it for general purpose measurements, like lab measurements, You can set up your camera and look at a cart rolling along, or looking at a pendulum swinging, or whatever. Here's a bicycle going by. And you can take measurements and then bing, 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 figure out speeds and accelerations and all that good stuff,
It's kind of fun in a weird, nerdy way.
Yeah. So see this thing up here?
Yeah.
That's a little toy that spins around and leans out, and you can measure the speed of the little things, and study circular motion. So I study that using using Tracker. And then right next to this is that little Newton's cradle thing, touch balls, and you go click, click, and you can study that using Tracker and so forth. So I use Tracker in teaching, but that's why I had it. Comes to the top of my brain as far as, oh, hey, building coming down. I could measure that, and there it is. So that's where it is.
Great idea.
Right.
I'm glad you thought of it. Change the world. Now we just need everybody else to wake up.
Okay.
All right. Thank you so much.
Nice visiting.
We'll talk soon.